Math 2414, Calculus 2, Section 9.2, Calculus with Parametric Curves, Video 1 of 9, Tangents. Before we jump into the next section, let's quickly review the main idea from Section 9.1. Recall from 9.1 that a parametric curve is a graph, capital C for curve, whose ordered pairs are of the form x of t, comma y of t, where x of t and y of t are functions of t. For some values, a is less than or equal to t is less than or equal to b. Translation. Every point on the graph can be calculated by taking some value for t between a and b, sticking it into two separate functions, and those functions calculate the ordered pair. Prior to parametric equations, it was almost always, we'll calculate the y value if you give us an x value and tell us what to do with it. And now in this context, it's, we'll calculate both the x and the y values if you give us a t value and tell us the two functions to calculate x and y. The equations x equals x of t and y equals y of t are called parametric equations, and t is called the parameter. And it is worth reminding you that the parameter can be any variable. Generically, t usually represents time or something like that, but there may be other contexts where we're measuring something else, such as the angle of rotation, in which case our parameter could be something to represent an angle like theta. But if we're going to talk about tangent lines and their slopes, then we need to figure out how can we calculate the slope of a tangent line of a curve if all we know is the function that generates the x-coordinate and the function that generates the y-coordinate. If you recall back from Calculus 1, the derivative dy dx would tell us the slope of the tangent line, but this is assuming that we had something like y equals f of x. In other words, give me a function, I'll take its derivative. Well, we're not defining our functions in the standard way of saying y is a function of x, or one variable is a function of the other. We're defining our functions parametrically, meaning that every point on the curve requires two functions to define it, one to calculate the x-coordinate, one to calculate the y-coordinate. But we still want to know what the slope is. So how are we going to get this, dy dx, when we have x as a function of t and y as a function of t? And the answer is we're going to go back to the chain rule. Now the chain rule comes in a lot of varieties. And most of the time when we use it, we say do the derivative of the outside, leave the inside alone, and then multiply times the derivative of the inside. But there are other ways to write the chain rule, one of which looks like this. Let's say we want to take the derivative of y with respect to t. We can first take the derivative of y with respect to x, and then multiply the derivative of x with respect to t. Think of it this way. If we had y equals a function of x, but x was a function of t, then we would take the derivative by taking the derivative of the outside, that's this, leave the inside alone, and then multiply times the derivative of the inside. Well, here's our derivative there, here's our derivative of the outside, and here's our derivative of the inside. So using the chain rule, we get this relationship between three derivatives. The derivative of y with respect to t, which we can calculate if we have this function. The derivative of y with respect to x, which is what we want to know. And the derivative of x with respect to t, which again we can calculate if we have the function defining x. Well, anytime you have an equation and you want to know one thing and you know the other things, in theory you can solve it. Although I know that there are some equations that are technically impossible to solve. This one's not one of them. If I want to know what dy dx equals, all I have to do is divide both sides by dx dt. So we get this formula for dy dx. dy dx is equal to dy dt over dx dt. Which is easy to remember if you think of these as fractions, which they're not. But if you were dividing fractions, you would multiply by the reciprocal of the denominator and then cancel the matching dt's, leaving dy over dx. So visually there's a gimmick to remind you it's dy dt on top, dx dt on bottom. Now before we get into some examples, which we'll do in the next video, we need to talk a little bit more about the dy dt derivatives, the dx dt derivatives, and what they mean. For example, if dy dt equals 0, this means that our y-coordinate is no longer moving up or down. It's think of a ball bouncing ball, and dy dt is measuring its velocity, because that's what derivative measures. When would the velocity be 0? When you hit a high point, or when you hit a low point. If it were, think of an oscillating sine curve. My y is not going up, my y is not going down. Every time my y pauses and changes directions, or at least has a velocity of 0, my y's derivative should be 0. In other words, if dy dt equals 0, then the graph should have a maximum or a minimum, but in terms of tangent lines, means the graph has a horizontal tangent line. Well, that makes sense. Previously, when we put the derivative in equal to 0 and solved it, the graph had a horizontal tangent line because it hit a maximum or a minimum. It's kind of the same thing here without regard to the x-coordinate, just thinking about the y moving up and down. But what if dx dt is equal to 0? And by the way, this is true if dx dt is not equal to 0. Standard fare, don't let denominators be 0. But what if it is? If dx dt equals 0, this is measuring how fast my x-coordinate is changing. So it's doing the exact same thing that the dy dt did, just in the x direction. In the dy dt, whenever it was equal to 0, that means we hit a high point or a low point, because our velocity had to hit 0. I say high point, low point, you could hit a flat point, meaning that you go up, you slow down, you stop, but then you keep going up again. So the better thing to say is horizontal tangent line, not high point or low point. There may be one, but it may be a flat point. It's the same thing with dx dt. If this is measuring how fast my x-coordinate is changing from left to right, then what happens when my graph hits a dx dt value of 0? That means my velocity in the x direction is 0, which means the point pauses, and sometimes it'll turn around, go the other direction, or it'll pause and then keep moving. But either way, you have a vertical tangent line. Then the graph has a vertical tangent line. A vertical tangent. Now, both of these are assuming that the derivatives aren't 0 simultaneously. So both of these have an unless dy dt equals 0 and dx dt equals 0 simultaneously. Then what? Well, if we run into that situation, we'll talk about it. But for now, we'll assume that if one derivative is 0 but the other one isn't, then the one that is 0 tells us that we have a horizontal tangent line or a vertical tangent line, depending upon which one is equal to 0. Before we move forward to the next video, I also want to briefly talk about the second derivative, because second derivative tells us concavity, so we can learn things there. So how can we find a formula for the second derivative, which we could write d2y over dx2? Well, think about what it means to take a second derivative. It means to take the derivative of the first derivative. So it would be the derivative of dy dx. So dy dx, if you will. But we're doing everything in terms of t. So we would need to use the chain rule again, or rather use this rule again that says if I want to find a derivative with respect to x, it's the derivative with respect to t over the derivative with respect to x. So this on top would be the derivative with respect to t of dy dx, which if we found this first derivative, then we already know what it is in terms of t, so finding this derivative in terms of t is pretty straightforward. And then dx dt. So what this means is if you're finding the second derivative parametrically, and you found the first derivative using this formula, you don't find the second derivative by just taking its derivative again. Its derivative will be up here, divided by dx dt. So to find the second derivative, it's the derivative of the first derivative the one we would have found first using that formula, divided by the derivative of xt. So you don't just do the derivative again. You do that and then divide it by the derivative of x. All right, in the next video, we're going to demonstrate some examples. In the next videos, I should say. But most of them are going to use this formula. To find the slope of the tangent line, to find dy dx, we simply calculate dy dt divided by dx dt.